Our next speaker will be Thomas Wade from Geotech with a whole bunch of co-authors on there. His talk is ZTEM VTEM Airborne EM and Magnetic Results over the Lalor Copper Gold VMS Deposit Region. Thomas is a graduate from Simon Fraser University. He's employed in the airborne geophysical exploration industry, leading survey crews around the globe for AeroQuest and Geotech. Thomas is an expert in the acquisition, quality control, and processing of airborne magnetic, radiometric, and electromagnetic survey data for mineral exploration targets.
1 second, everybody. Some stuff hot off the press here. Oops, I just closed the thing. Damn it. Where was that? Sorry. Messed up. So let me just load it in. Yep. Right here. Yep.
All right. I'm going to do one of these guys. All right. So I'm going to present Geotech's ZTEM and VTEM Airborne EM and magnetic data from the Lalor Copper Gold VMS deposit. This presentation was mainly put together by Legault, Geoffrey Plastow, Nasreddine, Bournas, Shengkai, Zhao, and Alex Prikhodko. To start with a quick outline, I'll talk a bit about the location and geology of the Lalor Lake deposit, and then about the configuration of the 3 surveys that Geotech has completed in the area. In 2007 with the VTEM, in 2009 with the ZTEM System, in 2012 with the VTEMMAX. From these surveys, I'll first cover the results from the magnetic data before discussing the results of the VTEM and ZTEM surveys, and then get into some multi-parameter comparisons from 1D, 2D, and 3D inversions. So the Lalor VMS deposit was discovered in 2007 from a drill hole intersecting high-grade zinc mineralization, approximately 800 meters below the surface. We've seen this morning, with a Crone time domain electromagnetic anomaly from a survey in 2003. The same survey also identified a second target to the northwest of Chisel, which is the South Bullseye. So here is the deposit in plan view on the left and cross-section on the right, showing the drill hole locations and the zinc-rich ore body outlines. The deposit has a footprint of approximately 900 meters north-south and 700 meters east to west, with a vertical extent from 550 meters to 1,200 meters below the surface. So here's Alan Bale's simplified geology map of the area, with the location of the Lalor Lake, Chisel Lake, and South Bullseye VMS deposits. And the outline of the major intrusive complexes, the Richard Lake Pluton, Chisel Lake intrusion, that are outlined in black there. The VTEM survey in 2007 was carried out over quite a large region, and those are the survey lines overlaying there. The ZTEM survey was more focused on the Chisel Lake and Lalor Lake deposit, and then the VTEMMAX survey in 2012 focused mainly on the Lalor and South Bullseye deposits. So Geotech was contracted soon after the initial discovery in 2007 to fly a VTEM survey. The survey covered 1,742 line kilometers with 100-meter line spacing, and we used the 30 hertz base frequency with our newly added, at the time, B field measurement. We returned to the area when testing the ZTEM system in 2009. We first tested a small area with 100-meter line spacing and then expanded to a larger area with 200-meter line spacing, with a goal of testing the system's ability to map deep conductors. In 2012, we flew the area again as a test for the VTEMMAX large loop, large dipole moment system. However, the mine site development was already well underway at that point, so a lot of our signal was masked by mine site culture and power line noise. Technical information about the VTEM system as it was in 2007. We used a base frequency of 30 hertz for maximum depth penetration. The peak current of our trapezoid waveform had recently been improved, and with the 7.5 millisecond pulse width, we had a dipole moment of between 390 and 410,000 NIA on our 26-meter transmitter loop. Up the tow cable was a single cesium sensor magnetometer, and new for the system in 2007 was a B-field measurement and an improved signal-to-noise ratio, which allowed for excellent resistivity discrimination and a wide dynamic range of resolvable conductivities. We estimated at the time the depth of investigation of the system was about 400 meters. The VTEMMAX system was brought to market in 2012 with a larger 35-meter diameter transmitter. We fly it with a Koala helicopter with dual generators, which allows us to generate more current, about 360 amps on average, which brings the peak dipole moment up to about 1.4 million NIA. So the MAX system has a dipole moment about 3 times bigger than the VTEM system did in 2007, a peak current approximately 1.5 times larger, and a much better signal-to-noise ratio. We had tested it previous to this, over the Caber deposit, and had detected that at 650 meters, so we assumed that it would also detect the Lalor deposit. The ZTEM system, which was flown in 2009, is a passive EM method that utilizes the natural electromagnetic fields from worldwide lightning activity as a source of transmitted energy. The airborne receiver measures the vertical component of the AFMAG field, and we set up a fixed base station near the survey to measure the horizontal X and Y primary fields, which is the sort of square one there. We record 30, 45, 90, 180, 360, and 720 hertz frequencies, though it's common and during this survey as well that the 720 hertz is just not good enough. Via a tensor fast Fourier transform, we derive the X and Y axis tipper values. And the depth of investigation for ZTEM is approximately 1 to 4 kilometers for a highly resistive host, 300 meters to 1.5 kilometers for a moderately resistive host, and up to 400 meters for a weakly resistive host. The large depth of investigation and sensitivity to weak resistivity contrast makes the ZTEM really well suited to porphyry copper exploration and things like unconformity hosted uranium, though it hasn't been tested previously, or hasn't been widely tested over VMS deposits. So going to aeromagnetics, this is the total magnetic intensity with the outlines of the mapped Richard Lake Intrusive Complex and Chisel Lake Gabbro, which is RLIC and CLG on the map there, as well as the VMS deposit locations. There are mag highs along the Snow Lake Fault and the Photo Lake and Three House, so it's the PET and SLFZ. And here in the calculated first vertical derivative, we see weak highs over the Lalor VMS and Ghost Lake Volcanics, and the Chisel VMS deposit is not associated with a magnetic high at all. In these magnetic susceptibility depth slices from a UBC Mag 3D inversion, the 100-meter depth slice shows highs over the Chisel Lake Gabbro. It's weaker over the Richard Lake Intrusives, Photo Lake, Ghost Lake, Lalor, and the South Bullseye. As we go down to 500 meters and down to 1,000 meters, the magnetic susceptibility highs over both Lalor and the South Bullseye are absent, suggesting that the weak mag highs are associated with superficial cap rocks and not the VMS. This is a late-time DBZ DT image from the VTEM survey flown in 2007. So the strongest EM responses were over the Snow Lake Fault and the footwall mud sulfide horizons, which is FMSH on there. There are shallow conductors present in the footwall units to the north, but the Lalor VMS and Chisel deposits did not appear as anomalies. The Lalor VMS and the South Bullseye are both coincident with a long wavelength anomaly, which could indicate that deeper alteration that we've been talking about. The late off-time time constant, or tau response from the 2007 survey shows the highest conductances over the Snow Lake Fault and the footwall mud horizons, and shallow VMS units north of the Lalor Lake deposit. However, the Lalor deposit itself is not anomalous. The 400-meter depth slice, if I can go down there. The 400-meter depth of investigation of the VTEM system in 2007 appears to have been insufficient to resolve the deposit. In these apparent resistivity depth slices from the Geotech 1D RDI, the slice at 100 meters shows lows over the Snow Lake Fault Zone and the footwall mud sulfide horizon, as well as north of Lalor and a zone northwest of Chisel, which is that South Bullseye again. The 400-meter depth slice, which is there, shows an unexplained conductive zone that expands across Lalor and the south bullseye, possibly indicating that alteration at depth again. So we're going to move on to the VTEMMAX. This is the late-time DBZ-DT grid from VTEMMAX in 2012, and for the most part, the results are identical to the 2007, except for the cultural contamination from the power line and the metallic objects now around the deposit at the surface. So there's still the long wavelength anomaly that extends from Lalor to the south bullseye to Chisel. The late-time Tau grid is also similar to the 2007 VTEM survey results, except again for that cultural overprint on the Lalor deposit. There remains a strong high over the Snow Lake Fault and the Lalor VMS as well, but the response from the Lalor is too shallow, and it's not seen in the 2007 data, so we presume it has to be superficial culture. A moderate to weak Tau anomaly extends from the south of Lalor to the bullseye and to Chisel, covering that conductive deep alteration zone. In resistivity depth image at 100 meters from the VTEMMAX, there's an apparent resistivity low over Lalor, as well as the conductive zone southwest of the south bullseye. At 500 meters depth, that resistivity low expands from Lalor towards the south bullseye, and then that continues in the 1,000 meter depth slice. So on the left is the RDI-1D profile across a line bisecting the Lalor VMS from the 2007 survey, and a coincident line from the VTEMMAX survey on the right. Shallow conductor is present that's not common to both the 2007 and the MAX surveys, so we assume that has to be due to mine site culture. The next set of profiles is across the south bullseye, and where the VTEM survey from 2007 bottoms out around 400 meters, the VTEMMAX detects the same buried conductive zone much below 400 meters. Thus, it must have sufficient depth of investigation to detect Lalor, but at the time of the survey, it's masked by that big pink blob underneath the power line. Switching to the ZTEM survey flown in 2009, these were the preliminary results following the November 2009 test survey. In the top left corner is the observed data across one line with the XIP and YIP profiles. A positive to negative crossover in the in-phase X tipper values is coincident with the Lalor VMS deposit, which is indicative of conductivity at depth. 2D inversion of these data using frequencies from 30 Hertz to 360 Hertz is shown in the lower left, and shows an area of low resistivity matching with the approximate extent of the Lalor deposit. After the success of this initial test, Hudbay extended the ZTEM survey over a much larger area with wider line spacing. In this 2D ZTEM inversion, the outline of the Lalor Lake ore body is overlain along with the drill holes and the conductive zone imaged by the ZTEM to about 1 kilometer depth, and it matches the vertical and lateral extent of the deposit. The ZTEM system was likely then the first airborne EM survey to resolve the Lalor deposit. These were shown, obviously, as a HUD-based slide. They were shown by them at PDAC in 2010, but not regularly thereafter. The 2D inversion of the ZTEM results in 2010 identifies the conductive response related to the Lalor VMS deposit, and underneath the power line noise, which is sort of the garbled stuff towards the south, is the rest of the Chisel horizon, which is also conductive, but the nature of the south bullseye was not widely studied yet. We didn't actually do further analysis on this data set until this year. So this slide shows the ZTEM in-phase total divergence, starting with this image at a higher frequency, 180 Hertz, which has a shallower skin depth. The total divergence converts crossovers into peaks using horizontal derivatives, so it attenuates long wavelength features. At the shallow depth imaged at 180 Hertz, the Snow Lake Fault Zone and the footwall mud sulfides are visible, but the Lalor VMS deposit is not differentiated from those shallow sulfides. At progressively greater skin depths, so here's 90 Hertz and 45 Hertz, Lalor and the south bullseye become distinct anomalies. This slide shows resistivity depth slices from a 2D inversion. At 100 meters, there are conductive anomalies over Chisel. the footwall sulfides and Lalor, and also minor anomalies southwest of Chisel Lake. As we progress to 500-meter depth slice and 1,000, there are well-defined conductive anomalies over Lalor and the south bullseye, which again agrees with that ground EM data. These are resistivity depth slices from a UBC MT 3D inversion with a coarser mesh than the 2D, and at 100-meter depth there are conductive anomalies over Chisel and the footwall sulfides, as well as zones west and southwest of Chisel Lake, but no conductive response over Lalor. But again, as we proceed to 500 meters and 1,000 meters, there are well-defined anomalies over Lalor and the south bullseye. So to summarize our results using multi-parameter cross-sections over the Lalor deposit, the VTEM2007 RDI on the top highlights a 1.5 kilometer wide resistivity low that's perched above the Lalor deposit, possibly clay-altered volcanic rocks or sulfide mineralization in the upper footwall units. The deposit itself is undetected at greater depths because it's simply below the depth of investigation of the VTEM system at that time. The VTEMMAX 1D RDI cross-section from 2012 features a similarly perched conductive layer above the deposit that's slightly wider and extends from 200 to 500 meters depth to below 900 meters, owing to the significantly larger depth of investigation for the VTEMMAX. However, a shallower, more conductive body is also resolved at approximately 50 to 400 meters, directly above where we would expect the Lalor ore body to be. And this northeast dipping thin plate conductor must therefore be related to man-made metallic structures from mine development that was underway in 2012. The Lalor deposit itself, though it's partially correlated with that broad, low resistivity half space, is undetected or unresolved as a distinct conductive feature at depth by our VTEMMAX survey, in spite of the fact that it is within our depth of investigation. The 2D and 3D ZTEM inversion results highlight a distinctive resistivity low that in the 2D correlates well with the actual depth extent, but is slightly broader to the east than the lateral width of the Lalor deposit. The 3D model resolves a more complex anomaly shape with a shallower, less than 1 kilometer wide, more weakly conductive body that correlates well with the VTEM zone, and a deeper, more conductive anomaly that correlates very well with the width, vertical extent, and if you get a little arm wavy, maybe even the dip of the Lalor ore body. In the 3D magnetic susceptibility inversion, the Lalor VMS deposit appears non-magnetic. However, the Ghost Lake, Rye Lake caprock appears to be weakly magnetic on top. This is a similar multi-parameter comparison for the sections across the south bullseye EM anomaly that lies approximately 1.5 kilometers southeast of the Lalor deposit, and though subeconomic, it's at a similar depth to Lalor. The Maxwell 3D plate model overlaying is derived from parameters from the VTEMMAX data, as well as from the ground EM modeling. So over the south bullseye, the VTEM 1D resistivity depth image resolves a 2 kilometer wide resistivity low, less than 120 ohm meters, that's perched above the south bullseye at about 200 meters depth and extends to 350 to 390 meters depth, the maximum for the VTEM survey, or the VTEM system in 2007. You can sort of pick out a subcropping, steeply dipping conductive zone sort of around here where the cursor is, but that's fairly poorly resolved in the 2007 results. The VTEMMAX 1D RDI shows a similar, about 1 kilometer, 1.5 kilometer wide body, resistivity low. That's slightly deeper than the 2007 data, but extends to depths close to the depth of investigation of the VTEMMAX, so 900 meters or so. The Maxwell plate model fits well within the limits of the wide conductive feature, and the subcropping conductive sulfide in that footwall rock is well resolved in the RDI. The ZTEM 2D and 3D resistivity models highlight a conductive feature buried approximately 400 meters, northeast dipping, and greater than 500 meters wide, extending below 1.5 kilometers depth. And here, like the VTEMMAX, these shallow footwall sulfide conductors are also imaged. The 3D magnetic susceptibility section shows that the south bullseye is non-magnetic as well, but those shallower sulfides in the footwall rocks are more magnetic, and that might be related to pyrrhotite. So to conclude, Geotech has conducted and studied 3 different airborne EM surveys in 5 years over the Lalor Lake deposit. The Snow Lake VMS deposits are mostly non-magnetic, and Lalor escapes detection below a weakly magnetic caprock in our magnetic inversions. The 2007 VTEM depth of investigation of about 400 meters isn't sufficient to resolve the Lalor deposit, but the clay alteration is visible. The ZTEM survey in 2009 appears to confirm the depth and vertical extent of the Lalor deposit in 2D and 3D inversions. The VTEMMAX survey in 2012 was unsuccessful in resolving the Lalor deposit as mine site development and power lines masked any conductive signal. However, the clay alteration was again visible. And VTEMMAX and ZTEM agree well over the south bullseye stringer sulfide in 1D, 2D, and 3D inversions. Thus, the VTEMMAX should otherwise be able to resolve the Lalor deposit. And that's all I have.
Questions?
No? Sure.
What's the status of the ZTEM or ZTEM system today? Where is it?
We have several of them, about a dozen. So we have helicopter-based ZTEM systems that we fly pretty much everywhere. And we also have a fixed-wing ZTEM system now that we can also put a gravity gradiometer with, or magnetic survey or radiometric survey with. And the fixed-wing ZTEM is also flying. Yeah.
Excuse me, got the numbers. So the question is, how do you calculate the resistivity in ZTEM when you're only measuring the magnetic field?
That would be a question for Zhao in the RDI or the inversion process for ZTEM. I'm mostly the preliminary guy.
Yeah, go ahead.
Just curious how the inverted results compare with the well logs.
In the ZTEM or VTEM?
Both the magnetic susceptibility and the resistivities.
I'm not sure if that's been compared by us yet. Whether the actual susceptibility or resistivity or conductivity values have been lined up with the well logs. That's another thing that I'd have to investigate with Zhao.
All right, thank you very much.